Assalamu alaikum. We will solve some problems together on chapter 14. Here he says a solid aluminum ball or a solid aluminum sphere with a volume 0.005 cubic meter is suspended in air in a scale as shown in the figure. The scale reads 320 Newton. So this is the real weight. So the real weight, which is mass times gravity, equals 320. The sphere is then totally submerged in liquid. So when you put it in the liquid, of course, the apparent weight will decrease because the water applies an upward force, which is the buoyant force. Okay. So we have the weight of the ball, which is mass times gravity, and we have the buoyant force, and the difference in between the two forces is the reading of the scale with an unknown density. So the density of this liquid is unknown. The scale reads only 212 Newton. So we said the reading of the scale equals the weight, which is 320, minus the buoyant force. So this is 212. So we make an equation now. What is the density of the liquid? So we need to find the density. From this equation, 320 minus buoyant force. Buoyant force equals what? The density of the liquid times the submerged volume, which is given 0.005. So this is submerged, times gravity, which is 9.8, equals 212. So I will substitute submerged volume 0.005. Gravity will be 9.8. So I will find the density of the liquid. So let's do it together. So 320 minus 212 equals 108 divided by 0.005 divided by 9.8. So the result is 204.08, okay, of course, kilogram per cubic meter. So this is the density of the liquid. Okay, let's see something else. A typical hot air balloon has a volume of 2,992 cubic meter. So this is the volume of the balloon. Okay, and we consider the balloon in the air as a submerged volume. The balloon volume is submerged volume in a liquid. Of course, this is not a liquid, but it's a fluid, okay? And gas also is a fluid. So this gas is considered as a fluid, and we can apply the buoyant force equations on the fluid. So the density of the air outside the balloon is 1.18. So the density of the fluid outside, which is the air outside, equals 1.18 kilogram per cubic meter. And the submerged volume, which is the volume of the balloon, is 2992 cubic meter. The density of the hot air inside the balloon, the density of the air inside the balloon, equals 0.93 kilogram per cubic meter. How much weight can the hot air balloon lift? We need to find this weight, the weight that the balloon can lift. Okay, so we have here the weight of this box. Let's call it box, or load, or whatever. Let's call it load. And there is also the weight of the balloon itself. And there is the buoyant force upward. So these three forces are balanced forces. So I can say the buoyant force, which is upward force, equals the weight of the balloon plus the weight of the load, which is the box. This is what I'm searching for, the weight of the load. So I can say the weight of the load equals the buoyant force minus the weight of the balloon. What's the buoyant force? Density of the fluid, which is the outside fluid. It's comparable to the water if there is something inside the water. So outside times the submerged volume, which is the volume of the balloon. This is the submerged volume, times gravity. So this is the buoyant force, minus the weight of the balloon, which is the mass of the balloon, times gravity. And I don't know the mass of the balloon, but I can say the mass of the balloon equals what? Equals density of the air inside the balloon times the volume of the balloon. So the mass equals rho times V. Okay? So we can rewrite it as density outside, density of the air outside, times volume of balloon times G minus mass of the balloon itself is the density of the air inside times the volume of the balloon times G. So we can take V times G as a common factor. So V of the balloon times G times rho, which is the density outside air, minus rho for the inside air. Of course, you can calculate it from the beginning with numbers, but I want to reach to an equation. Then we can solve this equation, or we can substitute in this equation. So all of this will give you what? The weight of the load. So what's the volume of the balloon? It's 2992 cubic meter times G, which is 9.8, times the difference in densities. The density outside is 1.18 minus density inside 0.93. It will be very easy to find the answer. Let's try to do it together. 2992 times 9.8 times 1.18 minus 0.93. The answer is 7330.4 Newton, of course. So this is the weight of the load that this balloon can lift. Okay? So again, I applied the balance equation. The force upward, which is the buoyant force, equals the loads, which is the weight of the load plus the weight of the balloon itself. The weight of the load is the one I'm searching for, while the weight of the balloon is the mass of the air inside the balloon times the density, the mass of the balloon itself, which is the mass of the air inside the balloon, equals the volume of the balloon times the density of the air inside the balloon, as we did here. So this is the mass of the balloon times gravity. And the buoyant force is the density outside. The buoyant force always is the density of the outside fluid, which is here also air. Okay? So the density of the air outside times the volume of the submerged object. The submerged here is the volume of the balloon. The same. Okay? Times gravity. So this one times this one times this one. Then I took a common factor, volume times gravity. The leftover is rho outside minus rho inside. Then I substituted to find the weight of the load. Let's move to something else. An iceberg, Jebel Galidi. Usually the iceberg, part of the iceberg is above the water, but most of the iceberg is under the water. Okay? So, and that's a problem for the icebergs actually, that only very small part of the iceberg is seen above the water, while most of the iceberg is under the water. And that was the problem of the Titanic ship. Okay, in the Titanic ship, they didn't see the iceberg because most of the iceberg was under the water. Okay, only very small part was above the water. I think they didn't see it. It was at night or something like that. Okay. So the iceberg of a mass 5.26846 kilogram, very large, floats in the ocean water. Calculate how much volume of the iceberg is visible above the ocean. So I need to calculate the visible volume, this part only. Okay, this part only. V visible. Take care. The volume under the water is the submerged volume. This is the submerged volume. If you add the visible volume to the submerged volume, it gives you the total volume of the iceberg. And this is the key of the solution, that the submerged volume plus the visible volume, it gives you the total volume of this iceberg. Let's continue. Calculate how much volume of the iceberg is visible above the ocean water. Note that the density of ice of this iceberg is 890 kilogram per cubic meter, while the density of water, density of the fluid outside, which is the fluid or the ocean water, it will be a little bit more, which given here 1030 kilogram per cubic meter. So how to solve this problem? Here I have a balance equation also. The buoyant force upward equals the weight of the iceberg. Okay, so the buoyant force equals the weight of the iceberg. Okay, what's the buoyant force? The density of the outside fluid, which is the density of the ocean water, times the submerged volume, which is the volume of the ice under the water, times gravity, equals the weight of the iceberg. The weight of the iceberg is the mass of the iceberg times g. Of course, we can cancel g with g. But how to get the mass of the iceberg? It's made of ice. So it's the density of the ice times the total volume of the iceberg. The density of ice times the total volume of the iceberg. All the volume under and above the water. Okay, so we can say density of the ocean water times V submerged equals the density of ice times the volume of the iceberg. What are the information given here? I know the density of ocean and I know the density of ice. They are given. What else? The mass of the iceberg is given. So this mass is given. So we can calculate, we can say this first equation is equation number 1. We can solve equation number 1. Of course, G will be removed with G. the mass of the iceberg is given, the density of the ocean water is given, so I can calculate the submerged volume. So I don't need the second part here. I don't need it. Okay, you can cancel it here. So density of the ocean is 1030 times V submerged, I don't know it, equals the mass of the iceberg 526846. So V submerged equals let's do it 526846 divided by 1030. So that's 511.5 cubic meters. So this is the submerged volume, of the iceberg. We need the what? We need the visible volume. Okay, so we need to calculate the total volume first. We need to calculate the total volume of the iceberg. V total. The total volume of the iceberg equals what? We know that the mass of the iceberg equals the density of the ice, as we said, times the total volume of the iceberg. So total volume equals the mass of the iceberg, 526846, divided by the density of the ice, which is 890. So this is the total volume. We can calculate it. It's also 526846 divided by 890 gives you 591.96 cubic meter. So now I have two volumes. The total volume, which I got it from this equation, and the submerged volume, which I got it from the first equation. I can say the visible volume equals total volume minus submerged volume. So 591.96 minus 511.5. So that gives us 80.46 cubic meter. Okay, which is the right answer here, 80.41. So as you can see here, the total volume is 591, but the visible is only 80 cubic meter. Like most of the volume is submerged under the water. So the sailors and the ships need to take care of the icebergs. It's very dangerous. Okay. So if we calculate the percentage here, like I'm done with the problem, but if I'm trying to calculate the percentage, 80 divided by 591.96 times 100, that's like 13% only. 13% of the iceberg is visible above the water, while 87% is hidden under the water. So that's why it's very dangerous for the ships to approach the icebergs, especially at night. Let's see the last one. A steel ball. Let me remove this problem from here. Let me take it somewhere else. A steel ball is suspended in the air by spring scale. The scale reads 8.2 kilogram. So this is the real mass of the ball. 8.2 kilogram. This is the real mass. If the suspended steel ball is fully submerged in a tank of water, similar to the previous problem, okay, I will submerge it in water. So in this case, I will have the weight, okay, the real weight, which is mass times gravity, and I have buoyant force. Okay, if I subtract them, this will give me what? This will give me the reading of the scale. Exactly similar to a previous problem. So the reading of the scale is the difference between the real weight and the buoyant force. What will be the new reading of the scale? But take here, he asks for the new reading in kilogram. So he doesn't need it as Newton. You need to divide the reading after you find it in Newton. You need to divide it over 9.8 over G, because he needs it as kilogram here. So the water density is 1000 and the steel density is 8000. So I will say the reading as in Newton, this is the reading in Newton, is the weight, the real weight, minus the buoyant force. What's the real weight? The mass of the steel times gravity, minus buoyant force, the density of water times the submerged volume, which is the total volume of the steel. This is the volume of the steel because it's totally submerged, times gravity. Okay? Of course, if we divide over gravity, we will get the reading in kilogram. So if I divide over gravity, I will get the reading in kilogram. So it's mass of the steel minus rho of the water times the submerged volume, or the volume of the steel itself. So now I divided over G to make it easier. What are the information here? I know the real mass of the steel. The real mass of the steel. So it's given 8.2. 8.2 minus density of the water, also given 1000 kilogram per cubic meter, times volume of the steel. I don't know the volume of the steel, but I know the mass of the steel and I know the density of the steel. So I can say the mass of the steel equals the density of the steel times the volume of the steel. Or I can say the volume, also I need the volume, so the volume of the steel equals the mass of the steel ball divided by the density of the steel. So I can say here the volume of the steel equals the mass, which is 8.2 kilogram, divided by the density of the steel, which is 8000. Substitute. Let's do it again together. So 8.2. Of course, you can take 8.2 common factor, but I don't want to make it complicated. Minus those three zeros with the zeros, so it's 8.2 divided by 8 in brackets. So the result will be 7.175 kilogram. So this is the reading of the scale in kilogram. So I hope you understood these problems. Okay? And if you need any other problems, please let me know.